distinct pleasure to have with us an invited speaker, Dr. Judith Irwin, for whom the members of the Kingston Center have a tremendous amount of admiration. I'd like to call upon Christine Kulik to introduce her.
Hi. The Kingston GA Committee were extremely delighted when Dr. Judith Irwin accepted our invitation to present the paper at this GA. From talks that we've been fortunate to have her present to our local center in the past, we know that listening to Judith describe some of the work that she's doing in the area of galactic structure is an experience that can expand our view of the cosmos and get us thinking about new and wondrous possibilities. Dr. Irwin is an it's too early in the morning for me. Dr. Irwin is an assistant professor of physics here at Queen's University, and she's worked at astronomical research facilities around the world during a career in astronomy that began in the 1970s. Judith is fondly known to many RASC members across the country, having been very actively involved in public astronomy education activities in places like Edmonton and Toronto, as well as Kingston throughout her career. She's a person of amazing energy, a researcher, a university professor, mother of two wonderful youngsters. She has an astronomy column in a local Kingston newspaper and regularly organizes free astronomy education activities for the public here at Queen's. And she is a great and true friend to the Kingston Center of the RASC. It's my very great pleasure to introduce Dr. Judith Irwin.
Thank you very much, Christine. That was very nice of you. I'd like to say that the RASC has been a wonderful friend of Queen's as well. I'd like to start this presentation with a very short video.
That's you?
Yep.
Nice one, sir. Thanks. Man, I'm stuffed. Me too. I ate like a pig. Hold on. You are a pig. Oh, right. Timon? Yeah? Ever wonder what those sparkly dots are up there? Oh, I don't wonder. I know. Oh, what are they? They're fireflies. Fireflies that got stuck up in that big bluish black thing. Oh, gee. I always thought they were balls of gas burning billions of miles away. But with you, everything's gas. What do you think? Well, I don't know. Oh, come on, come on. We told ours. Please.
Well, somebody once told me that the great kings of the past are up there, watching over us.
Really?
You mean a bunch of royal dead guys are watching us?
I guess that stopped rather abruptly. But today I would like to ask a question very similar to Pumbaa's. Ever wonder what those fuzzy, spirally patches are up there? Perhaps they are like island universes, separated from each other by a huge expanse of interstellar nothingness. Perhaps they are like open boxes, communicating with each other, interacting with each other. Or Simba might say that perhaps they are spinning wheels, spinning the luminous hair of the great kings of the past. Today we know that they are galaxies, but the degree to which those galaxies are independent of each other is still an open question. I would like to argue today for galaxies as open boxes, and I would like to present to you just some of the evidence that suggests this. Galaxies come in two main flavors, and now that we have more and more observations of galaxies, we're finding that there are many more types than we ever really imagined. But we still tend to think of them as falling into two main groups. The elliptical galaxies are one kind, such as you see here, N87, and they tend to be spheroidal systems with very little cool gas in them, and mostly composed of stars, as much as we can see at optical wavebands. And then there are the beautiful spirals, like NGC 2997 here. And the spirals are also large systems of stars, but the stars are confined to a thin disk, at least thin with respect to their diameters. And in the spiral galaxies, we tend to see a number of other components which are not so easily seen in ellipticals. For example, the dark dust bands, and Terry Dickinson showed you an example of some of this last night. And there are some hot gaseous regions called H2 regions up here. So let me focus. Okay. So we still tend to think of galaxies as being either spirals or ellipticals, and I think the one thing that you might notice as you look through a telescope at a galaxy like this, I'm sure everyone here has done that, is how isolated they certainly appear to be. You look at one galaxy and then you have to search for a while somewhere else to find another, and in and of themselves they seem to be distinct, very distinct entities. But if you look a little closer, you start to see that they're not as alone as you might have thought. Here's M31 with a couple of companion galaxies nearby it. These are actually separate systems as well, but they tend to cluster. They cluster around the larger systems. And so often a very large galaxy will have a number of small companions. Well, again, if we keep on going with this, we find that galaxies, even the large ones, tend to cluster around each other as well. And here we have a negative of the Virgo cluster, and the elliptical galaxy I just showed you previously is the one down here. And there are a number of other spirals and ellipticals in this field. And so you can actually see that galaxies cluster together, and even clusters of galaxies tend to cluster together. And so there's a hierarchy involved. But suppose we go back to the nearby universe and just take all this into consideration. The fact that some galaxies are isolated, and some galaxies are in groups, and some galaxies have companions, and ask what's sort of a typical separation between galaxies? Well, let's do that. For a galaxy, let's take a typical optical diameter, which might be about 10 to the 23 centimeters. And if you aren't familiar with scientific notation, that's a 1 with 23 zeros. So I don't know why astronomers use CGS units, but they do. 10 to the 23 centimeters is sort of the size of a galaxy, such as the one I showed you. That's about how far it would be across. But the typical separation, and of course this will vary depending upon environment, but a typical separation between galaxies is ordered the same thing to maybe 10 to the 25th centimeters. In other words, if we compare the separation between galaxies, nucleus to nucleus, with the size of a given galaxy, we find a ratio of about 10 to the 0 to 2, or about 1 to 100 or so on average. And that's not a very large number, astronomically speaking, actually. So in other words, galaxies look far apart, but they're actually close together. Now let's compare this to stars. A typical diameter of a star, like the Sun, and the Sun is quite typical, is perhaps 10 to the 11 centimeters. Typical separation between stars is in fact probably a little higher than this, but I just took sort of the Sun to its nearest companion, and it's about 10 to the 19 centimeters. And so now if we compare the ratio of the separation of stars to their diameters, we get a rather large number, about 10 to the 8. And so as you look out at the Milky Way and you see so many stars close together, in fact, they're not close together at all. Stars look close together, but are in fact far apart. And so, now as we ask ourselves, what is the probability of interaction? Well, I'm not going to give you a number here, because the number will vary depending again on the environment. But I think you'll agree that the probability of two galaxies colliding is significantly higher than the probability of two stars colliding. So now if we go back and look at our groups of galaxies, now if if we go back and look at groups of galaxies, we start to see some rather interesting things. Here we have a little group with a spiral galaxy here, and there's another one. And we start to see some rather interesting features coming out of the galaxy, which look a bit like spirals, but in fact they're more like polar rings. And here's a very interesting example of two galaxies which actually are in the process of merging. And even as you look at this picture and see the light burnt out in here, you have to remember that the stars are not colliding because the separation between stars is really very large. But the gravitational fields of the two galaxies are affecting each other such that the whole thing's getting messed up. Now, this sort of thing has been seen for some time. In fact, it was the 60s that Falta Mark started to develop his catalog of peculiar objects and found many such galaxies. And it has given people a chance, especially since the development of computers, the very fast improvement in computers, to be able to model such effects. For example, here is the antenna, and there are two very long tidal tails, and there are two aspects of this merging galaxy. And this can be actually modeled quite nicely by assuming that you start with two normal disk galaxies, having them collide, and then seeing the distortions that result, and the end product resembles what you actually observe. And of course, you have to put in the mechanics properly to do this. So galaxies do collide, and they do merge, but then what happens? If they merge, do they always just end up as a mess? Well, let me show you a series of images. This is a galaxy called NGC 7252, and what you're seeing here are three snapshots of different exposures. This is a short snapshot, so you can see there's a bright nucleus. A longer exposure shows the elliptical shape of the galaxy, and a little bit longer starts to show the spheroidal nature of this elliptical galaxy. And if you studied the properties of this galaxy, you would find that they are exactly the same as any other elliptical galaxy. Now let's go a little bit more and expose yet again. As you go to a longer exposure, you go from C to D, and A to E here are all the same spatial scale. Now you can see that there is all kinds of stuff associated with this galaxy. There are arcs and loops, and it's obviously undergone a traumatic experience recently. And this is burnt out again. Now here in F we have a different spatial scale, but here you can see the full galaxy with the tidal tails, and this is clearly the product of two merging galaxies. But the interesting thing is that what we found here was that at the center of this galaxy, the thing looks just like an elliptical. Now this has been modeled as well via computers, and it's found that the whole picture is fairly consistent, that when two spiral galaxies merge together, they can turn into an elliptical galaxy. Eventually they can settle down. And so not only can we see that galaxies interact, they can merge and they can change their form. And this dramatically changes our view of the evolution of galaxies. Here's just a sequence of different kinds of galaxies. Everyone sure will recognize M51 in different stages of interaction. And on the top left, we start with a mild interaction, so there's still strong spiral-like features, and there's the companion, through various interaction strengths, and we finally come to the most highly interacting, which is the one I just showed you, 7252. It is fairly clear now and accepted by most astronomers that these processes occur. It is not clear whether this is the only way to produce elliptical galaxies. There could be other initial conditions which have effect as well. And besides that, you might say, well, that's fine, galaxies do interact with each other, but what about those galaxies that you still see sitting by themselves that don't show any of these features? They don't show any particularly strong interaction. They seem to be by themselves, minding their own business. And this is a galaxy which I'll show you in a moment, NGC 253, which might fall into that category. Well, things get more interesting for the isolated galaxies when we start to look at other wavebands. As you know, the human eye and optical telescopes only observe in a very tiny fraction of the electromagnetic spectrum, just in here. And maybe we can detect a little bit in the infrared or ultraviolet with ground-based detectors. But there's a lot of other information that we haven't received yet in many cases, and they come from wavebands which extend from the ultraviolet, X-ray, and gamma rays, and the infrared through to the radio. Now, the thing I want to point out here is that all of these wavebands can only be observed from space. And so every iota of information that we have of those wavebands have been acquired within the last 3 decades. And if you compare that to the millennia that human beings have been observing in optical wavebands and through optical telescopes for several hundred years, you will see that there's a lot of catching up to do. Over here in the radio, there's a bit longer. The time band goes to about post-World War II, when radio astronomy started out. But still, the vast majority of observations today and throughout history have still been done in optical wavebands. And we're finding that at other wavebands, you see some very, very interesting things. For example, here we have an elliptical galaxy. It looks a bit strange because there's a dust band across it, and so this is not such a great image, but the dust band makes it look bifurcated. But otherwise, it's a fairly ordinary elliptical galaxy. Now, if you look at this galaxy at radio wavelengths, this is what you see. The optical galaxy that I just showed you fits in about there, around this dot. And what you see are 2 enormous radio lobes on either side. Now, the emission that's happening here is called synchrotron radiation, and it occurs from very high energy electrons spiraling around in a magnetic field. And what's happening is there's probably a supermassive black hole at the center of this galaxy, and the jets are emanating in either direction from the black hole. Now, this isn't to talk about black holes, so I'm not going to linger on this. But you get the idea that there's a lot of emission out here which is being ejected into intergalactic space from that galaxy, which you would never have suspected if you just looked at it optically. There are many, many more examples of this. Here's a couple more, and here you can see some rather different shapes of the lobes, and there's a good example of a nice long jet which clearly connects the lobe to the nucleus. Now these images tell you something else, which isn't perhaps immediately obvious, and that is that this can't again be all that's here. There has to be what's called an intergalactic medium. There has to be at least some gas permeating this whole region of space, because if there were not, you would not see this at all. The reason you see this lobe is because the jet is coming into some pressure equilibrium with the surrounding gas, and there's a lot of energy loss and dissipation here, and so therefore you will see it as a bright lobe. So just by detecting these kinds of ejecta, this led astronomers to understand that there must be an even larger medium surrounding galaxies that again is not apparent optically. Now you might ask, is there any direct evidence for such a medium? And the answer is yes, but you usually detect this medium at X-ray wavelengths because the gas is extremely hot. It tends to be around 10 million degrees Celsius. And so it emits in the X-ray regime, which, as I've said, we've only started to observe over the last few decades. So here's an example, and of course we don't have very good spatial resolution yet either for X-ray emission. This is an A-bell cluster, and most of the dots you see here are optical galaxies. And the contours are contours of X-ray emission, which center on the brightest, most central galaxy in the cluster. And here you will see there's an enormous amount of gas in this cluster that is being detected at X-ray wavelengths. Now, it has been the case that such gas has only been observed in very massive clusters. But I think that's due to the fact that the detectors simply aren't sensitive enough to detect it in other smaller systems. And just a couple of years ago, the new ROSAT satellite, which is an X-ray observing satellite, detected similar gas in a very, very small group of galaxies. The IGM revealed call this. And here you just see a couple of galaxies. Sorry for the quality of this overhead. You just see a couple of galaxies here, and I think there's a few more in this group. It's just a very small group, and yet you see this permeating X-ray emission around these galaxies. Well, where does it come from? Where does the X-ray gas come from? And the answer to that question is not really known yet. Whether, for example, there was some residual material left over when the galaxies formed, or whether the gas came from the galaxies. But you know that some of the gas had to come from galaxies because it is enriched material, which means that some supernova must have put some heavier elements into this gas. So there's been some recycling of gaseous material. Remember the galaxy I just showed you as being isolated, NGC 253? This is what it looks like in the X-ray. It's the same galaxy. There's its optical disk, and there are the X-ray contours. What's going on here, it is believed, and this is actually a very early, as you can see, 1993, this is all reasonably new. What seems to be going on is that there's a very bright starburst in the center of this galaxy. And when you say there's a starburst, that usually means that there's a lot of supernova going off, a lot of hot young stars with massive stellar winds, and they are just blowing all this material out, perpendicular to the main disk, which is the path of least resistance, forming these huge arcs and possibly being the major source of the intergalactic medium that I just showed you. Well, I've had the fortune of looking at a few galaxies in different wavebands. And so I'll just show you a couple of them. Starting with M108, which I'm sure many people here have observed before. It's in Ursa Major. And it is a well-known optical galaxy. And I looked at this galaxy with a graduate student, Denise King. And we observed in a line of neutral hydrogen. Now, neutral hydrogen is a spectral line. And when you observe in neutral hydrogen, it's very useful because you can use the Doppler effect to tell you the velocity of the gas. By looking at how much the frequency shifts of the line, that tells you the velocity of motion of the gas, whether it's going away or towards you, just like the usual whistle coming by the train that changes pitch, and you can get a velocity from that, or from the guys waiting on the highway for you. Now, what we did was, when we looked at the neutral hydrogen, we just added it all up to see what the neutral hydrogen around this galaxy looked like. And this would be cool gas, so it's about 100 degrees Kelvin, or about 170 or so degrees below 0 Celsius. This is the neutral hydrogen envelope in contours, overlaid on the optical image. Okay, there's the same optical image I just showed you in a different contrast. And you can see that the neutral hydrogen forms an enormous envelope around this galaxy. This is a loop here, that's actually a hole of emission right there. There's a loop, there are extensions coming away from the disk into the halo of the galaxy for sure, and possibly the intergalactic medium. And there's a very long extension here. And if you take a look at this feature, I mean, it's as long as the galaxy's radius at least. In other words, it's a border 28 kiloparsecs or so, or maybe 60,000 light years. Now, what we've done is we've isolated just a few frequencies, which means we're going to now look at just the gas that's on this side of the galaxy advancing towards us. This galaxy is rotating, so the gas on this side is coming towards you, the gas on that side is going away from you as it rotates. So let's isolate those channels and see what they look like. Now, what you see is some of the gas on the advancing side of the galaxy. Now, remember, the whole galaxy is receding from you. So when I say advancing, I mean with respect to the center point where it's rotating. So it's doing this. Okay? So there we have here, this is a hole again, is a huge loop. Okay? This would be a bright emission here, and there would be a hole of emission there. So what we see is a very huge loop of material, which is one slice through an expanding shell. You can tell by the velocity of the structure that you have an expanding shell of gas, presumably formed somehow from the galaxy itself. Maybe from a very bright star-forming region there, but in fact, when we actually look at the star formation in the galaxy, we don't find any evidence for massive star formation in that position. So perhaps there's something else again going on that's producing that loop. Maybe magnetic fields are going to be important. But the point here is that you have these huge expanding shells of gas going out away from the galaxy and possibly into the intergalactic medium. I'll just show you one more in terms of the galaxies I've looked at, and that's NGC 5775 and 5774. Now here's NGC 5775. It's an edge-on disk, so it just looks like a line in the sky. And here's its companion, NGC 5774, which is mostly face-on. And they look fairly close together, but there's no strong evidence optically that those galaxies are actually interacting. Now, a few years ago, this galaxy and its companion were observed by three people named Hummel, Beck, and Detmar, and they published a paper on the radio emissions. This would again be the high-energy electrons we're looking at now. And they published this map of the galaxy. So you can see there's that edge on disk, and there's a few little fingers coming out of the plane, which were interesting. And so I worked with Ned Durick and Hans Bloemen, and we put some data together and got much more sensitive data. Now what we're using is the Very Large Array, or VLA, radio telescope in New Mexico, which is the best telescope in the world right now for dealing with this kind of an observation. And we decided to observe in a bunch of different configurations of the array and to put all those data together to get the most sensitive observations we possibly could on this galaxy. And I'll show you the result. This is what we found at the bottom. The optical galaxy would fit in about here, and the radio continuum emission forms an enormous halo around the galaxy. In fact, it almost looks like an elliptical system in the radio. There's the companion galaxies here. We also picked up emission from the companion. There's the emission around it, and there's a bridge connecting the two. They're obviously interacting. Out here we find some very interesting structures which are dynamic in appearance. They don't look relaxed, they look dynamic, as if to say that there's more yet to come here. It hasn't relaxed yet. So there's energetic particles are streaming up in this direction, and the distance between the plane center and out here is about 16 kiloparsecs, so that's about 50,000 light years or so. Now, the point I want to stress here was that the more you look, the more you find. We are not yet at a point, in radio astronomy certainly, where we have reached any kind of limit at all. And you might ask now, we've seen all these examples of galaxies interacting and communicating with their environments, and that there's intergalactic medium, but does every galaxy do that? Does every galaxy interact? And the answer is simply not known yet, because we don't have enough, well, people working in the field, we don't have enough time on telescopes to be able to survey large enough numbers of galaxies to do it. But the capability is there. And the time will come when we'll be able to answer this question. Remember him? When Rafiki tried to show Simba, he tried to tell Simba to look into the pool to see his father. And Simba looked, and all he saw was himself. And Rafiki then gave him some advice. And the advice was the following. I believe that's exactly where we are now. If we are going to definitively say all galaxies are open boxes, we need to look harder. And I think that in the next few years, certainly in the next decade, we will see examples of instruments coming online which will help us do just that. In fact, the VLA right now, you could do it if you could get enough time. But that's not too likely. The next telescope to watch over the next decade in radio astronomy is this one here. It's a giant meter wave radio telescope in India. And it is built now, and they're just in the process of getting maps out. And it will be like having 4 VLAs together. It will have, the surface collecting area is about 4 times that of the Very Large Array. And so keep your ears and eyes open for news on this within the next few years, because you may be hearing more about it. Thank you very much.
presentation. We have lots of time for questions. Michael?
This that last telescope, whose telescope is it and who runs it?
It belongs to India. They run it, they built it, and they paid for it. And it is actually a very low-cost telescope because they're concentrating on the low frequencies. And what that means is you can have an open mesh rather than a filled dish, which has to be very accurate to like micron accuracy. They can use a filled dish, which is not extremely accurate at the high frequencies, but very good at the low frequencies. So it's not an expensive telescope.
And where in India is it located?
It is located 80 kilometers north of Pune, which is 180 kilometers to the east of Bombay.
If I could put a supplement to Mike's question, I think Dr. Judith Irwin is going to be using that facility within the next year, correct?
Yes.
And moderator's privilege, maybe, could you expand on that?
I'm taking a sabbatical leave next year, starting in May next year, and I'm going to Pune to spend time with this telescope.
Wonderful.
I may have to help debug it. You should clap for my family because they agreed to go.
Here.
Could you comment on Ark's observation that sometimes two apparently interacting galaxies have greatly different radial velocities?
Yes, that's a very interesting point. This has been a controversy ongoing for some time in astronomy. Arc and a few others have observed quasars, mainly, point-like believed to be associated with galaxies right next to normal nearby galaxies. And the redshift, which implies the distance by conventional means, suggests that these are just line-of-sight objects, that the quasar is much, much farther away because it has a higher redshift. Now, Arc does not believe this because he claims that there are connections between quasars and galaxies. And actually, now that I've looked at some of this stuff, I'm wondering whether he might be seeing some of these evidence of outflows from the galaxy, which just superimpose. I think it's fantastic that there are people who really fight against the status quo and what most people think. The one argument which he has trouble with is, like, his argument is that these are actually things being ejected from the nucleus of the galaxies, right? And that the redshift is not giving you a distance, the redshift is giving you something else. The problem is that you never see blue shifts. And so if you have an object ejected from the nucleus of a galaxy in some random fashion, you would expect to see some of them coming towards you, some of them going away from you, and you always see the redshifted, the quasars are more redshifted than the nearby galaxy. So most astronomers believe that the quasars are just chance connections.
Will there be a website on your internet?
For GMRT, there is a website now. It's called the NCRA, the National Center for Radio Astrophysics. If you do a search on Pune, P-U-N-E, hopefully you should come up with it. And if you have trouble, see me after.
Back there?
In that last slide you showed NGC 5775,
Yes.
5774. The upper left and the lower right, there were small cells.
Yes.
Now, are the ACES streamers going towards the cells? Can you describe what the cells are?
Someone once said that science is a method of selective ignoring. But when you look at radio wavelengths, I'm not showing you the whole field here, but when you look at 20 centimeters at a whole big field, you see point sources everywhere. They are a nuisance. You want to get them out of the way because the side lobes from those sources cut across the galaxy of interest and distort the image. So some of these, I think that at least this one, now there is actually another galaxy down here, so there's a second galaxy, but at least this one I think is probably a background source. All of these could be background sources. But the fact that these seem to line up here is kind of interesting. I couldn't say in writing that they're connected, but it's just something to keep in mind the next time you see a galaxy and see the same thing.
Dr. Schmidt?
I'm very interested about what you said, when two spiral galaxies come together and they may form an elliptical galaxy. Do you have a reprint or something that I can look at that?
Actually, the one, 7252, was a PhD thesis by a fellow named Hibbard, Hibbard, and it's published, and probably his work is a good place to start. I think it's 1996. Again, see me after because
Okay.
somewhere I have that information.
Yes.
Is there any possible way that you would try to not be extra to our own galaxy, or is it?
Yes, it's been done, but as you can imagine, the problem with the X-rays is that people are not observing X-rays in spectral lines. In other words, it's a continuous emission across the X-ray band. You can just take a chunk out of it and see where it goes, but that means that you can't isolate any particular velocity. You have to just take whatever you get. So when you look through our galaxy, you can see stuff nearby, far away, whatever's in the line of sight, you'll get. And so it's really hard to say where certain structures are, where they are in comparison to others. And the best results so far suggest that hot X-ray gas permeates the disk of our galaxy and extends out beyond the disk to above and below the plane of several kiloparsecs, say 10,000 light years or so, above and below the plane. That's about the best they've done so far.
Paul?
Yeah, I'm wondering about the optical size of the galaxies you're showing. You've been showing images which show detail down towards the center of the galaxies. Ones that I've exposed many times show galaxies to be much larger than the sort of conventional pictures show. I'm wondering how the optical size is actually compared. If you go to the detection limit on relevant nearby galaxies, so the galaxies are bright, how do you find the size of the galaxy comparing to the detection limit with the radio size and so on?
Okay, you have, obviously the intensity, if you take a slice of intensity across the major axis, you will find the intensity will fall off in some fashion. And usually optically that is exponential. And so therefore you can define this size in different ways. One way you can do it is to define the exponential scale length. It goes to 1 over e at some number, and nobody can argue with that. It doesn't depend upon your detector. Now the other way is actually done most often in astronomy, is to use a catalog called the RC3, and in it are listed sizes of galaxies to an intensity limit, and that's 26 magnitudes per square arc second. 26.5 magnitudes per square arc second is the limit. That's pretty faint, people will agree. So I think we do pretty well in defining the optical disk. However, it is still magnitude dependent. It's still detector dependent. And in fact, there's a whole new field opened up called low surface brightness galaxies, where the whole surface brightness of the galaxy was faint and just wasn't seen above the night sky, and now they're being found all over the place. So,
in the beginning, you mentioned the distance between the galaxies is very small as compared to the distance between the stars. So the galaxies have no chance of running into one another. Now, since there are so many stars, there is a possibility that stars can hit one another. When the stars hit one another, what happens?
well, usually people don't talk too much about stars colliding unless they're talking about a binary star system, whereas two stars form together, close together, and there's actually contact and one's evolving and doing this. And the other example is where you might have a very dense cluster, star cluster, like a globular cluster in the core. Now this isn't actually my field of expertise, so I'm not sure I can give you the kind of answer you might want. But there have been some papers talking about fireworks that you can get when two stars coalesce. But I don't think the physics are extremely well developed at the present time. I mean, there's been some work done on it, but I think the work is still in the early stages, and I suspect there's a lot of debate amongst the astronomers as to just what does happen at that point.
How much of the mass of the galaxy might be gaseous phase?
That's a very interesting question. The mass of an optical galaxy, like our Milky Way, is about 10 to the 11 solar masses. A few times 10 to the 11 solar masses. That is the mass within that 26.5 magnitudes per square arc second radius, or diameter, right? Now, the gas usually constitutes about 5 times 10 to the 9. So it's a few hundredths as much of the mass of the optical galaxy. Most of the mass is actually of the stars. Okay? Now, even if you add on the envelope that extends beyond the optical disk, it still isn't, like the whole thing together is still, it would not go above 10 to the 10 solar masses. I would be very surprised if it did. So at the most, a tenth of the mass of the galaxy would be in that gas. But We all have heard of dark matter, and nobody knows what the dark matter is. And the dark matter could be hiding in very cold clumps of clouds. And then your question takes on a whole different meaning. If the dark matter is some form of gas, then the mass shoots way up.
One more question, keep it brief, please.
If some of the gas is reaching escape velocity, have you ever calculated how much mass the galaxy is?
Yes, I have. There's been a calculation done for our own Milky Way, which is believed to be losing about a solar mass per year. Now, in terms of the escape velocity, there isn't a lot of evidence that the gas reaches that value. So in other words, the gas could be going up into a very large dark halo and then coming back or dispersing or changing into some form. It may not be escaping completely into the intergalactic medium. So that isn't known, okay?
I'm sorry, that's all the time we have for
Okay.
questions.
I can try to answer better after.
Yeah, maybe we can meet afterwards. Deep appreciation of your wonderful presentation, and on behalf of all of the members of the RASC who are here, we'd like to offer you a very small token for this wonderful.
Oh, thank you very much.
Again, thank you very, very much.